Welcome to Introduction to Building Codes, Bangladesh National Building Code 2020, referred to as BNBC 2020, Part 8 Building Services, Chapter 6 Sanitary Drainage, Part 2 Drainage and Venting Requirements. The description of this course is as follows. This presentation is designed to familiarize and assist code officials in locating, describing, and applying the applicable code requirements for drainage and venting requirements. Also, this will assist designers, engineers, and architects regarding drainage and venting requirements as well. Our course overview. Internationally, code officials recognize the need for a modern, up-to-date plumbing code that addresses the design and installation of plumbing systems through requirements emphasizing performance. This presentation will cover key topics of the following areas: purpose and scope, terminology, permits, design considerations, installation of drainage systems, installation of venting systems, and design of drainage and sanitary systems. The goal of this training is for you to learn and apply key code requirements contained in Chapter 6, titled Sanitary Drainage, to enhance your performance while inspecting these systems. This training will also provide participants with specific code requirements with examples related to design, installation, and inspection of drainage and venting systems to further enhance your knowledge. Our course objectives are as follows. Upon completion, participants will be better able to locate general topics in Chapter 6 Sanitary Drainage, locate applicable codes and standards for specific situations, apply code requirements to real-world situations, as well as explain the intent behind a given code requirement. And finally, use good judgment to identify certain systems and related components as compliant or non-compliant. We utilize the code as a guide for not only the design basis of a system regarding sanitary drainage and venting, but also the installation requirements for a safe system for the end user. Sanitary drainage. Some general information is indicated here. The purpose of Chapter 6 is to regulate the materials, design, and installation of sanitary drainage piping systems, as well as the connections made to the system. Now, this could be the drainage piping that carries the wet portion of the discharge, as well as the venting portion, which provides an atmospheric pressure into the system as well. The intent is to design and install sanitary drainage systems that will function reliably, are neither undersized nor oversized, and are constructed from materials, fittings, and connections whose quality is regulated by this section. Plumbing fixtures installed in a building or structure must connect to a sanitary drainage piping system, and that system must connect to a public sewer system or private disposal system. The conventional method of sizing a sanitary drainage system is by drainage fixture units, abbreviated DFU. These are load values. The drainage fixture unit approach takes into consideration the probability of a load on a drainage system. The drainage fixture units allow us to properly estimate the capacity of pipes that are constructed for our drainage system. Section 6.1 is titled Purpose and Scope. The purpose of this chapter of the code is to provide requirements and minimum standards for the planning, design, and installation of waste disposal systems in and out of buildings. The authority has the responsibility for administering the code to ensure that waste disposal systems in homes and the buildings in which people live and work are designed, installed, inspected, and tested to provide acceptable waste disposal functions. Additionally, the proper design and installation of waste disposal systems, according to Chapter 6, provides a level of protection regarding health, safety, property, and public welfare. This initial section of the code gives the authority that ultimate responsibility for administering this code to ensure public safety. Section 6.2 is titled Scope. This section gives us the requirements whether the application fits this code or not. When we look into section 6.2.1, it indicates the following. This chapter specifies the general requirements for environmental sanitation for different categories of buildings according to their occupancy classification. We further look on to the next section, which is section 6.2.2. This chapter also covers the design, installation, and maintenance of drainage systems together with all ancillary works such as manholes and inspection chambers used within the building and from the building to public sewers or to off-site waste disposal systems. In other words, into septic systems and seepage pits or subsurface drainage systems. Finally, Section 6.2.3 tells us that the disposal of waste from industries, nuclear plants, slaughterhouses, etc. are not covered by this code. These wastes shall be properly treated as specified by environmental quality standards of Bangladesh before their disposal into public sewers or into natural bodies of water. The summation of these three sections give us the requirements set forth to scope our applications. It tells us in the beginning of the code that this chapter contains general requirements for environmental sanitation for different types of buildings that we will look at according to their occupancy classification. It also covers the design and installation and maintenance of these drainage systems, as well as the omission of industries, nuclear plants, slaughterhouses, etc. are not covered by this code. So this section gives us the driving language to understand when we are in the code or out of the code with respect to our applications. Section 6.3 is titled Terminology. This section provides an alphabetical list of all terms used and applicable to this chapter of the code. In case of any conflict or contradiction between a definition given in this section and that in any other chapter or part of the code, the meaning specified in this chapter shall govern for interpretation of the provisions of this chapter. This spells out clearly that the terminology contained within this section is very specific to our study today on sanitary drainage systems. The terminology actually has a specific meaning and shall govern the interpretation accordingly. A code provision could be misinterpreted if the definition of a term, as used in the context of this code, is not understood. The following slides will provide key definitions that will assist the code user to properly understand certain terminology related to this chapter. Codes, by their very nature, are technical documents. As such, literally every word, term, and punctuation mark can add to or change the meaning of the intended result. This chapter contains several terms that are important to understand the provisions of this code. Definitions are found both in this chapter and throughout the code. So let's look at some key terminology. The term building drain gives us an identification of what this particular segment of the building drainage system is. It is defined as the building drain is that part of the lowest piping or open channel of a drainage system, which receives the discharges from soil, waste, and other drainage systems inside the walls of the building and conveys the same to the building sewer, beginning at 0.9 meters outside of the building wall. As you can see, the graphic at the bottom of the slide indicates the building drain as being the lowest piping indicated within the building. It then extends 0.9 meters from the outside of the building wall. That is where the building drain ends. From that point, the next part of the piping system is titled building sewer. The building sewer connects from the end of the building drain and ties into the sewer main in the case of this graphic. By definition, the building sewer is as follows. The building sewer is that part of the horizontal piping of a drainage system which extends from the end of the building drain and which receives the discharge of the building drain and conveys it to a public sewer, a private sewer, individual sewage disposal system, or other point of disposal. This is also known as sewer. Lastly, the term public sewer. This is a common sewer directly controlled by public authority, also known as main sewer. As you can see, definitions are very specific, and in this case, it lays out the demarcation of where one system begins, one system ends, and the connection between the two distinct systems. The term branch is defined as any part of the piping system other than a main, riser, or stack. So anytime we see the term branch within Chapter 6, we need to think of definition giving us the specific meaning of that term. A circuit vent is the venting of branch piping with which multiple fixtures are connected in a battery. As an example, a circuit vent is a means of venting multiple fixtures using only one or two vents. The horizontal drainage branch actually serves as what we call a wet vent for the fixtures located downstream of the circuit vent connection. That means it conveys wet portion of discharge as well as a major portion of air within the piping system in the horizontal drainage pipe. In the drawing below, you can see that we have two circuit vented applications here tied together. This is called a series connection. The first circuit vented branch can be seen on the right-hand side. The dark solid line indicates the wet portion of drainage into the horizontal branch. This is an application of where we have multiple water closets, a battery of water closets that may be connected to a horizontal drainage system. From the last water closet on the far right-hand side to the next water closet, you can see our circuit vent rises vertically between those two connections. The vent rises vertically on the horizontal drainage pipe. This is what we call the circuit vent for battery 1. Now downstream, we need to size the piping accordingly to pick up the second circuit vented branch. In other words, we're adding 6 more water closets onto this battery. Again, between the first water closet on the second circuit and the next one downstream, we have another circuit vent that rises vertically. This is a multiple circuit vented branch. Branch interval. The length of soil or waste stack corresponding in general to a story height, but in no case less than 2.5 meters, within which the horizontal branches from one floor or story of a building are connected to the stack. One branch interval corresponds to a length of drainage stack that has 2 horizontal branch connections at least 2.5 meters apart. As seen in the graphic to the right, we have 2 different floor levels. Based upon these 2 different floor levels, we are concerned whether the piping arrangement indicated on both sides of the soil or the waste stack is considered a branch interval. To the right-hand side of the soil or waste stack, we can see that the measurement from the horizontal drainage pipe below floor level 1, the soil or waste stack rises, in this case, 2.5 meters or more to the next horizontal drainage pipe tied to the soil or waste stack. When this happens, this is considered a branch interval. Again, meeting the definition. In no case less than 2.5 meters. So the distance is a function of how the drainage system will work and be loaded up in the system, as we will find out later in our design examples. To the right side, we indicate that this is a branch interval. If we look to the left-hand side of the soil or waste stack, we see that the elevation from floor level 1 to floor level 2, the upper floor, has a 3-meter story height. Therefore, if we have any connections, as we do here, we have 2 horizontal connections into the soil stack on the left-hand side. The vertical distance measured is 1.3 meters between these horizontal connections into the soil or waste stack. This is not considered a branch interval. Does not meet the definition. As we recall, it must in no case be less than 2.5 meters. In typical multi-story construction practice, typically with 2.5 meter ceilings, horizontal branches connect just below each floor level to a vertical stack. Branch intervals are a design factor for drainage pipe sizing and venting. Drain, waste, and vent system design must consider the nature of waste, airflow in a stack, and the effects that branch connections have on such a flow. The branch intervals are a design factor, of course, and we need to understand exactly where they occur in the systems. Branch vent. The vent connecting one or more individual vents with a vent stack or stack vent. Stack vent is defined as a stack vent, we sometimes call a waste vent or soil vent, is the extension of soil or waste stack above the highest horizontal drain connected to the stack, also known as soil vent. As we see the drawing below, the definition of a branch vent again indicates the vent connecting one or more individual vents with a vent stack or stack vent. The branch vent in this case is highlighted in red. As you can see, the very last fixture on this drawing rises up with an individual vent. Upon the connection of the second individual vent from the fixture located downstream, this is where the branch vent begins. Again, it connects one or more individual vents with a vent stack or stack vent. In this case, we connect multiple individual vents along the way, creating our branch vent and ultimately tying this branch vent into the stack vent as shown. This is an example of branch vent connecting into the stack vent. A few other terms are described graphically here according to our drawing. Our drawing depicts a soil stack that rises from below to take the discharge from the horizontal branch accordingly. We have a washing machine, a laundry tub, and a kitchen sink that discharge into the horizontal branch, as well as the dashed line being the venting system. As we look at different parts of the system, we will start off with the definition of stack. A stack is the vertical main of a system of soil, waste, or vent piping. General term, we just need to understand what the term stack means in general. In this case, we have a soil stack. It is properly defined as its function, soil, and meeting the definition of stack. The next definition, horizontal branch. A horizontal branch is a drain pipe extending laterally from a soil or waste stack or building drain with or without vertical sections or branches, which receives the discharge from one or more fixture drains and conducts it to the soil or waste stack or to the building drain. There's a lot of information in this term. However, when we go back to our drawing, the horizontal branch is properly defined here. as it does take waste from the fixture drains located above the horizontal branch. The washing machine, the laundry tub, and the kitchen sink are all fixture drains that discharge into the horizontal branch that ultimately connects into the soil stack. Therefore, the horizontal branch is properly defined here in the drawing. Last is what we call vent stack. Vent stack is defined as a vent stack being a vertical vent pipe installed primarily for the purpose of providing circulation of air to and from any part of the drainage system. In the case of our drawing, we can see that the vent stack is completely piped in through the roof level of the building, allowing atmospheric air to be introduced into the piping system through this particular connection into the venting system of our sanitary drainage system. Fixture unit. A fixture unit is a quantity in terms of which the load-producing effects on the plumbing system of different kinds of plumbing fixtures are expressed on some arbitrarily chosen scale. That arbitrarily chosen scale, however, is somewhat well-defined based upon probability. The conventional method of designing a sanitary drainage system is based on what we call drainage fixture unit load values, abbreviated DFU, or simply fixture units can be used to define this particular loading probability. The fixture unit approach takes into consideration the probability of load on a drainage system. Just like any system, we're concerned with respect to the demand of the system. Once we understand the demand of the system or certain parts of the system, we can understand and apply and analyze piping sizes for different parts of the system as a basis of design. The DFU is an arbitrarily used loading factor assigned to each fixture relative to its impact on the drainage system. To further understand this value, we look at the DFU values determined based upon the following: average rate of discharge by a fixture, the duration of a single operation, and the frequency of use or interval between each operation. This is what goes into the fixture unit number, are these particular factors. Horizontal pipe is defined as any pipe or fitting which is installed in a horizontal position or which makes an angle of less than 45 degrees with the horizontal. When we look at the drawing below, we can see a pipe designed as a horizontal branch or horizontal branch drain. Looking at this particular pipe, we can verify that this is properly defined as a horizontal pipe according to the definition. A vertical pipe is any pipe which is installed in a vertical position or which makes an angle of not more than 45 degrees with the vertical. Again, looking at our drawing, we have a pipe called a water riser. We can see the water riser is a vertical pipe as well as the stack indicated on the left-hand side of the drawing. The stack and the stack vent, which rises above the stack, are vertical pipes, and they meet the definition accordingly. plumbing system is defined as a system of potable water supply and distribution pipes, plumbing fixtures and traps, soil waste and vent pipes, and sanitary and storm sewers, and building drains including their respective connections, devices and appurtenances within a building or premises. Graphically, we can look at the plumbing system as a series of multiple systems. If we focus on the sanitary drainage portion of the plumbing system, in the lower left-hand side of the drawing, we start out with the public sewer or the main sewer. We have a pipe that is called the building sewer that attaches to the building drain pipe. This receives all of the waste at its lowest level, called the building drain, as we understand according to the previous definition. As we rise up on the building drainage system, we move up to different floor levels. As we move up to floor levels, the stack rises vertically. We have horizontal branches, or a branch in this case, that connects into the stack. As you can see, the dark solid line represents the wet portion of the piping system. Therefore, the stack rises up vertically and turns into what we call a stack vent. This is a typical look at the drainage portion of the plumbing system. Section 6.9, Design Considerations. We need to specifically understand certain designs, the requirements that go into designing and constructing the plumbing sanitary drainage system. Section 6.9.3 gives us different building drainage systems. The requirement here is as follows. For the design and installation for drainage piping, one of the following building drainage systems shall be adopted. 1. The single stack system. 2. The one pipe system. And 3. The two pipe system. Figure 8.6.1 gives us an illustration of the single stack system, which we will describe systematically. Figure 8.6.2 gives us a diagram of the one pipe system. And finally, figure 8.6.3 indicates a diagram of the two pipe system. Looking at these briefly, in summary, we can go back to the single stack system and observe that it is a single pipe with connections made directly to that single pipe, which serves both as a discharge means for horizontal connections and a main artery for venting or providing atmospheric air pressure into this system. The diagram of the one pipe system is illustrated accordingly, where we have a soil stack indicated on the right-hand side and individual vents that connect fixtures that tie into the soil stack horizontally. All of the venting ties into branch vents which run horizontally and connect into the vent stack. The diagram of the two-pipe system, by inspection, can be looked at as separate systems. However, they are interconnected with respect to the venting. On the far right-hand side of the two-pipe system, we can see a soil stack that receives the discharge from water closets on each and every floor level. That is an isolated stack for the water closets. The next stack is the wastewater stack in the middle that collects discharge from wash basins, sinks, bathtubs. As you can see, there are no water closets or urinals on this particular wastewater stack. In both cases, the venting is interconnected through individual vents and branch vents and ultimately connected to the vent stack, which is seen on the left-hand side of this diagram. To further understand our piping systems, we will go into further detail. Section 6.9.3, item A, indicates the following. Single stack system may be used with 100 millimeter diameter stack for buildings up to 5-story height. The fixtures in each floor shall be connected to a single stack for increasing the rate of discharge in the downward direction. So right here is the requirement and limitation for this particular type of piping system. This system is allowed for up to 5-story height, and it may be used with a 100 millimeter diameter stack. The recommended depth of water seal trap for the different fixtures shall be in accordance with Table 8.6.4. When we reference that table below, we will see that the fixtures are indicated on the left-hand side of the table, and the water seal requirements in millimeters are indicated on the right side. As an example, floor traps, the fixture that we call a floor trap, maybe a floor drain, must have a minimum water seal of 50 millimeters. Below the table is an explanation of a trap and where the seal is located for a trap. We have the inlet that comes in from the fixture discharging into the trap. As it discharges through the trap and goes up above the dip, as can be seen here, and then spills over into the weir, which directs it to the outlet. That distance from the top of the dip to the weir is what we call the seal. This is the vertical elevation that we need to maintain according to the table above. So if this trap was for a floor drain, we would have to make a distance, which we call a seal, of 50 millimeters. This was filled with water to protect the occupants of the building from any type of noxious odors and sewer gas migrating back into the building. And that is the function of our traps. We provide a water seal as a barrier to prevent these gases from entering our homes and buildings accordingly. As we continue our discussion regarding the single stack system, there shall be at least 200 millimeters vertical distance between the waste branch and the soil branch connection, while the soil pipe will be connected to the stack above the waste pipe. The size of the soil branch shall not be less than 100 millimeters. The horizontal branch distance for fixtures from stack and vents at the foot of the stack to avoid back pressure, as well as the vertical distance between the lowest connection and the invert of drain, shall be as shown in figure 8.6.1. As we can see, according to that figure, we have, in fact, the distances indicated as such. We have the 200 millimeter distance indicated under the bathtub. As you can see, we have a 50 millimeter diameter parallel branch introduced if the bath waste would otherwise enter the soil stack below the water closet. And we have our 200 millimeter distance. That being shown, the size of the soil branch, not less than 100 millimeters. As we can see, up at the top of the stack, this is a full 100 millimeter stack accordingly. The next section is section 6.9.3, item B, describing the one-pipe system. Where all types of waste from the building are desired to be discharged into a common sewer or into the same waste disposal system, a one-pipe system may be used. Figure 8.6.2 gives us a description of what this may look like. As you can see, we have 3 different floor levels. This is our diagram of the one-pipe system. Observe that the sink, bath, and wash basin fixtures are connected to the branch waste pipe, and each fixture is individually vented. Also observe that the water closets are connected directly to the soil stack by branch soil pipes. The water closets are individually vented as well. All branch vents are graded properly and connect into the vent stack at each floor level. As we can see, we have what's called the branch waste pipe that carries the waste from the sink, the bath, and the wash basin directly into the soil stack. The water closets are tied in or connected to the soil stack as well. We have individual vents off of each and every fixture. However, they are connected by means of what we call a branch vent that runs horizontally and connects into the vertical vent stack accordingly. This gives us a good, well-rounded one-pipe system that is properly piped in as far as the drainage goes and the vent to allow proper air into the system when designed properly. Section 6.9.3, item C. This is the two-pipe system, where the sullage from kitchen and bath will be dealt with separately, and where soil waste shall be discharged into septic tank or Imhoff tank, the two-pipe system shall be used. Figure 8.6.3 gives us the diagram. In this diagram, observe that the sink, bath, and wash basin fixtures are connected to a dedicated wastewater stack, and each fixture is individually vented. When we look at the diagram, again, we see that we have a separate soil stack that serves as the vertical discharge for water closets and urinals on different floor levels. The wastewater stack indicated in the middle, receives the discharge through the horizontal branch from fixtures like the sink, bath, and wash basin accordingly. Observe that the water closets and urinal are connected to the dedicated soil stack again. Additionally, all the branch vents are graded properly, and they are connected into the main artery for air that we call the vent stack. Section 6.9.5, Installation of Drainage System. A general requirement given to us in Section 6.9.5.1 indicates that all plumbing fixtures shall be made of smooth and non-absorbent materials, free from concealed fouling surfaces, and may be located in ventilated enclosures. This section is provided to direct plumbing fixture standard creators as to the core requirements that all plumbing fixtures must meet. As indicated in the code section, we cannot have anything other than smooth, non-absorbent materials for our plumbing fixtures. Most mass-produced plumbing fixtures for installation in accordance with the code have the design and quality regulated by the various standards as specified in the code. We want a smooth, clean, non-absorbent surface to direct any discharge within the fixture downward into the drain and convey it safely and according to this particular section. As seen below, we have an indication of a sink in this picture. The faucet on the top discharges water. This could be for hand washing. In a bathroom, we would want to take all of the contents that fills the basin and directly discharge it by a smooth surface downward into the fixture drain cleanly, and ultimately having a very good smooth surface for cleaning the bowl after each and every successive use of this particular fixture. That is the basis of this particular section here, is we need to keep the fixtures clean and sanitary by having their materials made of good quality and durability, and to be non-absorbent as well. Section 6.9.5.2 gives us a requirement regarding the slope of horizontal drainage piping. Whenever possible, all drainage systems shall be drained to the public sewer or private waste disposal system by gravity. Horizontal drainage piping up to 75 millimeters in diameter shall be installed with a fall of not less than 20 millimeters per meter, and for larger than 75 millimeter diameter, the fall shall not be less than 10 millimeters per meter. It is a good policy to design the system for the highest possible velocity. However, consideration should be given to the fact that high velocities in pipes with slopes greater than 20 millimeter per meter may cause self-siphoning of the trap seal. So when we read this section, the code user must be understanding of the fall regarding certain piping. Even at higher velocities, if we carry solids within the system that are suspended within our drainage piping, we need to make sure that the solids do not drop out of suspension due to the steep slopes that one may think is better in a drainage system because the solids will drop out of suspension and cause blockages. The code user, here's a note. Section 6.7 references Table 8.6.2 that provides minimum internal diameters of soil and waste outlets for specific fixtures. As we look at the horizontal drains, according to our graphic below, we have a 32 millimeter horizontal drain pipe for a wash basin. A fall of not less than 20 millimeters per meter is required. When we move to the right-hand side, we have a 100 millimeter horizontal drain pipe for a slop sink. We have a fall not less than 10 millimeter per meter regarding the larger pipe size. Referencing Table 8.6.2 titled Sanitary Appliance Minimum Internal Diameter of Waste Outlet in millimeters, we can see that there are two parts of this table. The left-hand side gives us soil appliances, while the right-hand side gives us waste appliances. If we look at item B, soil appliances, bedpan washers, and slop sinks, our minimum internal diameter of waste outlet is 100 millimeters. This table gives us this minimum internal diameter for these specific type of soil appliances. On the right-hand side of the table, waste appliances such as a wash basin, indicated in item B, must have a minimum internal diameter of 32 millimeters. Section 6.9.5.3, where conditions do not permit building drains and sewers to be laid with a fall as great as that specified, a lesser slope may be permitted provided the computed velocity in the drains will not be less than 0.6 meter per second. The maximum recommended velocity will be 2.5 meters per second. This velocity is often referred to as what we call the scouring velocity. However, this terminology is not to be understood as cleaning the entire inside wall of the drainage pipe. For example, if the velocity is too low, such as where a pipe is extensively oversized, or it is not installed with adequate minimum slope perhaps, the solids in the flow will tend to drop out of suspension and settle to the bottom or the invert of the pipe. When this happens, blockages occur in sections of our piping system, and this needs to be avoided. Therefore, proper analysis needs to be done when designing our drainage system and slope with consideration to the velocity of the contents being conveyed through our piping system. Section 6.9.5.4, soil pipe conveying any solid or liquid filth to a drain shall be circular with a minimum diameter of 100 millimeters. The waste branch from bathroom, wash basin, or sink shall be of 32 millimeter to 50 millimeter diameter and shall be trapped immediately beneath such wash basins or sink by an efficient siphon trap with adequate means of inspection and cleaning. The minimum recommended size of waste stack is 75 millimeters. As we see in the graphic below, we have a wash basin or sink. The drain of the fixture is connected to the inlet side of a trap. As indicated in a previous slide, we described the function of the trap that takes the discharge from the fixture through the inlet above the dip of the trap, and it spills into the outlet of the trap through what we call the weir. And again, we need to have a water seal. This particular section gives us the size in diameter for these particular fixtures. As seen here, we need to be 32 millimeter to 50 millimeter in diameter for any type of wash basin or sink according to this section. As well as the waste stack is given as a minimum of 75 millimeters as well. Section 6.9.5.5, the soil and waste stack shall be continued upward undiminished in size, 0.6 meters above the roof surface, when the roof will be used only for weather protection. That gives us a requirement initially if we use the roof not as an occupiable space. We have a minimum dimension of 0.6 meters above the roof surface. Where the roof will be used for any other purpose other than weather protection, the soil and vent stack shall run at least 2 meters above the roof surface, so that there shall be least possible nuisance. Section 6.9.5.6, soil and waste stack shall be firmly attached to the wall with a minimum clearance of 25 millimeters from the wall. All soil, waste, vent stack shall be covered on the top with cowl of same pipe material. As indicated in the graphic below, for example, we may have an occupied roof surface where people occupy a roof or a part of a roof. In this case, we need to make sure that any stack must be at least 2 meters above the roof surface. And according to section 6.9.5.6, we must cover the top of the pipe with a cowl of the same pipe material. Pipe cowls are installed on a vent stack, wastewater stack, and soil stack as indicated in the graphic. Section 6.9.6 is titled Installation of Venting System. Pressure fluctuations are often created by waste flow in the drainage system. The purpose of venting is to protect the trap seal of each trap and maintain equilibrium or partial equilibrium of the trap seal. Vents shall be designed to maintain maximum differential pressures at each trap of not more than 250 pascals. Venting is not intended to provide for the circulation of air within the drainage system. Pressure fluctuations are created by waste flow in the drainage system. As an example, when a trap seal is exposed to a lower pressure on the drainage side of the trap, also called negative pressure or partial vacuum, the water seal will rise and flow over the trap weir and into the drainage system. The example shows a trap with a water seal at an elevation exactly the same on each side of the trap. We call that equilibrium. At this point, the trap is at its full seal height. Thus, sewer gases or any type of negative pressure is not considered here. It is not happening in the piping system. However, we do have gradient pressures that may affect the trap seal. Therefore, if we have a 250 Pascal differential, we can still be assured that the trap will function accordingly. Given here, if we have atmospheric pressure pushing downward in our drainage system on the building side of the trap, we can see that we have a differential happening within the trap. As seen here, we still have a trap seal that will provide protection for the building occupants. This information is good to analyze, good to implement, and for protection of the public. Section 6.9.6.1. The vent stack or main vent shall be installed in conjunction with a soil or waste stack in a building. One vent stack may serve not more than 2 soil or waste stacks. When we have ventilating pipes, section 6.9.6.2, they need to be installed that water cannot be retained in them. They should be fixed vertically. Whenever possible, horizontal runs should be avoided. Ventilating pipe shall be carried to such a height and in such a position as to afford, by means of the open end of such pipe or vent shaft, a safe outlet for foul air with least possible nuisance. There is a lot being said in this particular section here. The first part of this gives us the requirement for vent pipes. They need to be installed that water cannot be retained in them. We want to pitch the pipes, if they're run horizontally, downward in the direction of the drainage system. This will help with any type of condensation or rainwater that may get into the venting system through the cowl, down into the soil stack, and possibly run into horizontal sections. Again, we want to pitch those downward in the direction of the drainage system and install them so they are not trapped and do not trap any water in the venting system. This will allow us to have a full diameter vent pipe at all times to circulate or bring in atmospheric pressure into the system. Again, to provide equilibrium for our trap seals. That is the function here of venting. Section 6.9.6.3. The building with building drains shall have at least one 100 millimeter stack or stack vent carried full size to outdoor air above the roof in accordance with section 6.9.5.5 above. Recalling 6.9.5.5, the soil and waste stack shall be continued upward, undiminished in size, 0.6 meters above the roof surface when the roof will be used only for weather protection. Again, we covered that in a previous slide. For weather protection only, we are given that minimum height that the soil and waste stack must be above the finished roof surface. However, as we recall, if the roof surface is being used as an occupiable space for people to walk on that roof surface and occupy it, then the soil and waste stack must run at least 2 meters above the roof surface. A further explanation of vent pipes regarding the installation where water cannot be retained in them is explained here. Vent pipes must be properly graded to prevent the accumulation of condensate or rainwater. Whether the vent pipe is graded back to the drain pipe served by the vent itself or another portion of the drainage or vent system does not matter, provided that the water is not trapped in the venting system, creating a blockage or partial blockage of the vent. This is the function of channeling either condensate or rainwater down to a location that it will be drained off accordingly and not prevent blockage. According to the graphic seen on the right hand of this slide here, we have a fixture vent in the first block. This is an acceptable means of properly grading the vent pipe downward towards the direction of the drain. What's not acceptable is the block below on the lower left-hand side. This is not acceptable. As you can see, the fixture vent that we call the individual vent rising above is properly rising vertically. However, on the horizontal run, it is improperly graded downward, not in the direction of drainage. This could cause a low portion in the piping to be completely filled with condensate or rainwater, thus causing the blockage and providing a barrier for air to properly enter the system. In the upper right-hand corner, an acceptable means of running a vent, in this case, above a kitchen sink. This is an individual vent rising vertically. As it is graded up on the beam downward, we grade the piping downward as it falls down below the beam and is still graded downward, sloping downward in the direction of the vertical vent coming off of the lav. As we grade those pipes downward in each case, any water will be channeled downward, not affecting the overall diameter and not causing any blockages in that portion of the venting system. What is not acceptable is in the lower right-hand block, described as such. Here is our kitchen sink. We have the dashed line again, which is our individual vent, running across longitudinally with the beam. However, in this case, the vent pipe drops down below the beam, goes across the beam, and then rises up vertically before tying into the lav vent that rises vertically. As you can see, there is a trap created here. This will provide a blockage with respect to any rainwater, condensate that will build up over time and thus eliminate any type of air in the system for this partial venting area. Section 6.9.6.3. The building with building drain shall have at least 100 millimeter vent stack or stack vent carried full size to outdoor air above the roof in accordance with section 6.9.5.5 above. And again, recalling what that section stated previously is the elevation that is a minimum needed for any soil and waste stack, even a vent stack or stack vent in this case, will have the minimum elevation of 0.6 meter above the roof surface when the roof is used for weather protection. Remember, we're in the venting installation part of the code here. So this section here is specific to vent stack or stack vent. We're getting a reference here back to section 6.9.5.5 regarding the elevation of the vent stack or stack vent. If we use the roof as an occupied roof surface, then in this case, either a vent stack or stack vent must be 2 meters above the roof surface. The diameter of a vent stack shall not be less than 50 millimeters, as provided in section 6.9.6.4. Another requirement that is very specific is the diameter of a branch vent pipe on a waste pipe, and this shall not be less than 25 millimeters or 2/3 of the diameter of the branch waste pipe ventilated. This is given to us in section 6.9.6.5. We are provided with very specific requirements in this portion of the code regarding dimensions of our vent piping. These are minimum sizes that are given to us accordingly. Section 6.9.6.6, the branch vent pipe on a soil pipe shall not be less than 32 millimeters in diameter. And again, the sections above provide specific requirements for minimum vent pipe sizes regarding vent stacks and branch vent pipes. This particular section, 6.9.6.7, gives us a lot of requirements. We will break this apart systematically. All main vents or vent stacks shall connect full size at their base to the building drain or to the soil or waste stack at or below the level of the lowest drainage connection to them. That particularly fits a definition accordingly, and the requirement tells us that it needs to connect full size here. Additionally, all vent stacks shall extend undiminished in size above the roof, or shall be reconnected to a vent header or to the stack vent portion of the soil or waste stack, at least 150 millimeters above the flood level of the highest fixture connection discharging into the soil or waste stack. Where the roof is to be used for any purpose other than weather protection, the vent extension shall be in accordance with section 6.9.5.5 as we discussed in prior slides. The graphic indicated on the left-hand lower section indicates an acceptable installation of vent rising at least 150 millimeters above the flood level rim of the highest fixture. The waste stack is indicated on the right-hand side that receives the discharge from this particular fixture. The function of the 150 millimeter rise above the flood level rim is for the function that we do not discharge any type of drainage into the venting system. This is that vertical rise that must be at a minimum above the fixture, which is 150 millimeters. As an example, if the drain blockage occurs where indicated here on the fixture drain outlet to the waste stack, The fixture will overflow before the fixture vent can conduct the waste flow to the stack vent. So this is a safety procedure by having this vertical elevation, so we do not discharge into the venting system. As indicated on the right-hand graphic, this is an improperly connected vent below the flood level rim. Now what happens here, as can be seen, the fixture vent does not rise 150 millimeters above the mop sink. It rises below and then ties in or connects to the vent stack. If there is a blockage that would occur in the fixture drain, as indicated in the dark area here, what will happen is it will take an alternate path. Rather than flowing through into the waste stack, the blockage will force the water to rise up vertically and enter the vent pipe, thus discharging downward into the vent stack. This is not permitted, and this is an example of an improperly connected vent below the flood level rim. Section 6.9.6.8. In case of offsetting of stacks, a relief vent shall be provided at the base of upper stack, just above the start of offset, and at top of the lower stack portion, just below the end of offset. This section requires venting offsets to reduce air pressure differentials. When we have horizontal offsets involving changes in the direction of flow from true vertical to greater than 45 degrees from vertical, we have a situation as indicated in the graphic. If we have a horizontal offset, we remember the definition of horizontal pipe. In this case, where we have a drainage stack and I have a horizontal offset, both the upper and lower section of the horizontal stack offset must be vented. High-rise buildings present a bit of a challenge. Section 6.9.6.9 gives us a requirement that in high-rise buildings, a yoke vent shall be provided at 10-story intervals counting down from the top. A yoke vent is simply an upright vertical Y connection to the vertical stack. The lower end of the relief vent is connected to the soil or waste stack below the horizontal branch that serves the floor level required to have the relief vent. As indicated in the drawing to the right-hand side, we can see that this occurs between the 11th and 10th floor. The location of this connection is intended to allow waste that might get into the relief vent, including condensation, to reach a waste line. This connection is made using a Y fitting installed as a drainage fitting in order not to impair the flow. The relief vent, as indicated, is constructed using these Y fittings. As we can see, the drainage stack, which is our solid line, comes up into the 10th floor. We take and install an upright Y connection into this vertical drainage stack and provide a bypass into the vent stack and tie into or connect into the vent stack with another Y fitting that is inverted in the other direction. This provides a good bypass for us to provide airflow or pressure differential into high portions of our drainage system. Section 6.9.6.14. Soil and waste stacks in a building having more than 10 branch intervals shall be provided with a relief vent. We will look at figure 8.6.7 at each 10th interval, counting from the top floor. This section gives us specific requirements of a method of relieving pressure conditions in drainage stacks that are more than 10 branch intervals in height. A relief vent must be located every 10 branch intervals. This is measured from the highest horizontal drainage branch, which is typically the top floor. The relief vent must be equal to the size of the vent stack to which it connects. Figure 8.6.7 indicates this condition, where we have a multi-story building, more than 10 branch intervals. We start from the top downward. Counting downward to the 10th branch interval, the relief vent is shown on the 10th interval below the top branch. As indicated in the enlarged plan, we can see that this occurs between the 5th floor and the 6th floor. The relief vent is properly piped in to allow this method of relieving pressure conditions in this particular application. And in each case, if this was a higher building, we would need this relief vent at every 10 branch intervals accordingly. The code provides us a method to connect several fixtures in a battery type of an arrangement. Section 6.9.6.10 gives us this particular requirement that is very specific. In case huge numbers of fixtures are installed in a battery to a single branch drainage pipe, circuit or loop vents shall be provided after 8 fixtures interval for 100 millimeter drain pipe and 24 fixtures interval for 150 millimeter drain pipe, as shown in figure 8.6.6. Circuit venting involves up to 8 fixtures in a single vent. A dry vent connects between the 2 most upstream fixtures on the horizontal branch. The horizontal branch serves as a wet vent for the battery of fixtures. Figure 8.6.6 shows 2 distinct circuit vent systems. As indicated, we have the main vent that rises up, which is our vent stack, and our circuit vents from both batteries ultimately connect back into the main vent. As we recall the definition of circuit vent, we will further discuss this system. Each circuit vented branch must be uniformly sized based on the total drainage load on that branch, including any drainage load from upstream branches. Circuit vented branches may connect either in series or in parallel. Each group of up to 8 fixtures must be considered as a separate circuit vented branch and be installed accordingly. The series circuit vented system, as shown in the upper graphic, indicates The one circuit vented branch indicated on the right-hand side of the drawing, we provide 1, 2, 3, 4, 5, 6, 7, 8 water closets on the one circuit vented branch. The dry vent that we call the circuit vent is connected between the last two upstream fixtures accordingly. When we move to the left-hand portion of this series circuit vent diagram, we have a second circuit vented branch that has a battery of 1, 2, 3, 4, 5, 6 water closets. And again, our circuit vent is connected between the two most upstream fixtures accordingly. The circuit vent rises up, moves horizontally to the right-hand side, and picks up the other circuit vent from the other battery of water closets being tied in series on the horizontal branch accordingly. This is called a series circuit vented branch. The parallel circuit vented branch is indicated as such, where we have two separate horizontal branches that discharge a battery of water closets. They are ultimately connected back into a horizontal branch that will get discharged, possibly to a soil stack. In this case, we look at the two circuit vented branches independently. We have 8 water closets, and just like the requirement indicates, we need to connect the circuit vent between the two most upstream fixtures on the circuit vented branch. In both cases, we have a circuit vent, which is our dry vent that rises up vertically and ultimately connects into the vent stack. Section 6.9.10, Grease Traps. Oil and grease is found in waste generated from kitchens and hotels, industrial canteens, restaurants, butcheries, some laboratories, and manufacturing units, having a high content of oil and greases in their final waste. This section is specific in that we must capture the grease prior to discharging into our drainage system. We must understand that. Waste exceeding temperature of 60 degrees Celsius should not be allowed in the grease trap. When so encountered, it may be allowed to cool in a holding chamber before entering the grease trap. This is for the specific function that when we cool down oils, it congeals, it solidifies to a point that it can be captured or drawn off in a chamber. Oil and greases tend to solidify as they cool within the drainage system. The solidified matter clogs the drain. Sand and other matter in the waste stick to it due to the adhesion properties of the grease. Oil and greases are lighter than water and tend to float on top of the wastewater. Thus, they are buoyant. Grease interceptors receive the discharge from fixtures and equipment with an effluent produced from food processing, food preparation, or other source where grease, fats, and oils enter automatic dishwashers, perhaps, with pre-rinse stations, sinks, or other appurtenances. An example below shows a grease trap or interceptor location where Grease and oils may be discharged from dishwashers, pre-rinse stations, or maybe food cooking operations, things of that nature, must be channeled down towards a grease interceptor or grease trap that removes the oil and grease prior to discharging it to the waste system. Grease traps shall be installed in a building having the above types of waste that we discussed in the previous slides. In principle, the grease-laden water is allowed to retain in a grease trap, which enables any solids to be settled or separated for manual disposal. The retention time allows the incoming waste to cool and allow the grease to solidify. The clear waste is then allowed to discharge into the building's drainage system. Now, the retention time allows the incoming waste to cool. There is a compartment that captures the grease that has been solidified and thus allows clean water to move through another compartment, not contaminated by any grease. That is the function of a grease trap in general. However, indicated below is an example of an automatic grease removal system. Through technology and innovative design, we've come up with more and more possibilities and applications to better allow us to draw off grease prior to discharging into the drainage system. In this case, this particular appliance will capture the grease as it solidifies into a chamber. Once the solidified grease is in this chamber, there is a timer and a heater that will heat up the grease in this particular chamber and allow a vacuum type system to draw off the now heated up liquefied grease into a reclamation tank. This will provide a storage for any grease that has been drawn off the system. Again, an automatic grease removal system. Oil interceptors are required by Section 6.9.11. They are required when we have oils and lubricants that are found in waste from vehicle service stations, workshops, manufacturing units, whose waste may contain high content of oils. Oils, for example, petroleum, kerosene, and diesel used as fuel, cooking, lubricant oils, and similar liquids are lighter than water and thus float on water in a pipeline or chamber when stored. Such oils have low ignition point and are prone to catch fire if exposed to any flame or a spark and may cause explosion inside or outside the drainage system. The flames from such a fire spread rapidly if not confined or fire vented at the possible source. Oil interceptors are a major concern. We need to capture the oil before being discharged into the drainage system. And the requirement of this section gives us some areas and occupancies such as vehicle service stations, manufacturing facilities that discharge oil to portions of our drainage system. This is a way of capturing the oil prior to discharging it into the sanitary system. An example of the oil separation system is indicated below. we have our oil separator, which appears in this graphic. From this point, we have a series of floor drains that are indicated here that discharge into the oil separator. The oil tends to float to the top. Thus, it is buoyant in the water. We have a draw-off pipe that channels the oil into the oil draw-off tank as indicated in the lower portion of the drawing. We have a suction connection extended to grade for maintenance and evacuation of the oil draw-off tank. As you will note, we have a lower outlet indicated on the oil separator. This is where clean water can discharge to the sanitary drainage system. As well, we have venting indicated according to the manufacturer of the oil separator, and we are venting any type of ignition, fumes, things of that nature completely to the outside of the building. To further understand and analyze the function of oil separators, lighter oils and lubricants are removed from the system by passing them through an oil separator. They are chambers in various compartments which allow the solids to settle and allow the oils to float to the top. The oil is then decanted in a separate container or containers for disposal in an approved manner. The oil-free waste collected from the bottom of the chamber is disposed in the building drainage system. The design criteria for effective performance depend on the minimum cross-sectional area and the minimum ratio of depth to width with respect to the oil separators. In turn, design and shape of the separator depend on the character and quality of the oils to be separated. The engineer must do an analysis of the environment and what types of oils will be entering this oil separator. Manufacturers have been designing oil separators for many, many years, and it is a good resource to gain information from manufacturers on their products for specific applications. A properly sized oil separator allows the separation and prevents the evacuation of solids into the drainage system. An example of an oil separator is indicated below. We have the inlet entering the oil separator into a compartment that has an adjustable weir. This is the first area that will trap heavy particles such as dirt, sand, and allow that to fall downward into the compartment, allowing clean water to elevate and discharge above the adjustable weir. This also controls flow as well. Once we are in the second compartment, this is where the parallel plate assembly allows the oil globules to separate from the water and become buoyant in this chamber. There is an oil skimmer that skims off the oil and discharges it to the oil draw-off tank that we saw in the previous slide. From the parallel plate assembly, due to the velocity of water flowing through, we may have heavier sludge particles that will settle out in the bottom of the tank and allow clean water to rise up in the third compartment with an adjustable weir again to adjust flow into the outlet of the oil separator. This is a simple process of capturing the oil particles accordingly. Section 6.10, Design of Drainage and Sanitation System. The very first section is section 6.10.1, titled Estimation of Maximum Load Weight of Wastewater. To estimate the total load weight carried by a soil or waste pipe, the relative load weight for different kinds of fixtures are provided in Table 8.6.12. Additionally, Table 8.6.13 provides an approximate rating of those fixtures not listed in Table 8.6.12. Let's take a look at this particular table. Table 8.6.12 is titled Fixture Units for Different Sanitary Appliances or Groups. This table identifies common plumbing fixtures with their corresponding fixture unit values. These values are used to determine the load on a drain, which in turn is used to determine the minimum drainage pipe size requirement for the load served. Again, you remember from the definition, fixture unit is an arbitrary number used on some arbitrary scale. But we can refine that. We can say it's a fixed number that is utilized to help us understand the demand of a system. In this case, we will break it down even further. The type of fixture is indicated on the left-hand side. If we pick a fixture such as a kitchen sink, domestic, we can see the fixture unit value as a load factor is specific and it gives us a value of 2. Remember, this is a probability of the discharge, the successive operations, and time of discharge for that particular fixture. It's a probability. However, we are given a factor called a fixture unit factor. We could utilize this to size the correct pipes for fixtures and multiple fixtures being connected to other parts of the piping system. We need to go to this table first to get the initial values for the fixtures as they start to discharge into the system. The next table that is indicated in section 6.10.1 is table 8.6.13. Table 8.6.13 is titled Fixture Unit Values for Fixtures Based on Fixture Drain or Trap Size. Now this table identifies fixture drain and trap sizes with their approximate fixture unit values. As seen in the table on the left-hand side, given is the fixture drain or the trap size. In a case of a trap size of 75 millimeters, this would equate to a fixture unit value of 5. This would be the demand of that particular diameter trap size. These values, again, are used to determine the load on the drain, which in turn is used to determine the minimum drainage pipe size requirement for the load served. Again, this table is for fixture drains and trap sizes, giving us the demand for those particular items. Designing a piping, we need to understand the velocity of the system. not to exceed a certain velocity for proper function. Section 6.10.2, Gradient and Size of Pipe. More specifically, Section 6.10.2.1 provides the requirement the building drains and sewer shall be sized to discharge the peak simultaneous load weight flowing half full with a minimum self-cleansing velocity of 0.75 meter per second. However, flatter gradient may be used if required, but the minimum velocity shall not be less than 0.6 meter per second. Again, it is undesirable to employ gradients giving a velocity of flow greater than 2.5 meters per second. This velocity is often referred to as scouring velocity. We recall this from before. However, this terminology is not to be understood as cleaning the entire inside wall of the drainage pipe. We need to keep in mind that grading the pipe, fall of the pipe, if the velocity is too low, such as where the pipe is excessively oversized, or it's not installed with adequate minimum slope, the solids in the flow will tend to drop out of suspension and settle to the bottom or the invert of the pipe, thus causing blockages in portions of our drainage system. So the engineer must properly design and analyze all parts of the system for good flow and velocity to convey the contents adequately and safely to other parts of the drainage system. Section 6.10.2.2 indicates a requirement: the maximum number of fixture units that may be connected to a given size of building sewer, building drain, horizontal branch, or vertical soil or waste stack is provided as in tables 8.6.14 and 8.6.15. Let's look at table 8.6.14 titled Maximum Number of Fixture Units that can be connected to branches and stacks. Looking at this particular table, the first column gives us the diameter of pipe in millimeters. The second column gives us the maximum horizontal fixture branch that can be tied into a given stack. That is our drainage fixture units. The next column, one stack of 3 stories in height or 3 intervals, is given as the stack, story, or interval accordingly. Again, these are the fixture units that we are to select from. We have the fourth column. This is where we have more than 3 stories in height. Total for the stack is given us the fixture units in that particular column for more than 3 stories in height. The very last column is the total fixture units for 1 story or 1 branch interval. As an example, using this table, 8.6.14, verify the bottom of the section of the stack for 1 branch interval. We apply the table utilizing the last column to the right, titled Total at 1 story or branch interval. From this point, we look at the drawing on the left-hand side. We have 1 branch interval. The total load on the bottom of the stack below both floor levels is as follows. We add up the total from the upper horizontal drain, 15 drainage fixture units, plus the horizontal branch on the lower level, another 1,500 drainage fixture units. Our stack for one branch interval must be able to carry 30 drainage fixture units. From that point, we go to the table, the very last column. We move downward until we hit 30 drainage fixture units or the next value greater. As can be seen here, we cannot use 16. We must go to 90. 90 drainage fixture units, and we move to the left-hand side. We come to any horizontal fixture branch. This value of 160 fixture units means that you cannot have any horizontal drain connected into the stack that discharges more than 160 on the horizontal connection into the vertical stack. In our example, we only have 15 drainage fixture units, so we are more than adequate of being lower than that value. That's our first check. Continuing over to the left even further, we can now size the pipe diameter of this stack for one branch interval as a 100 millimeter stack to carry 30 drainage fixture units for one branch interval. And that's how you apply this particular table for our example, one branch interval. Our next example, using this table, 8.6.14, we would like to verify the bottom section of the stack for 6 branch intervals. In this condition, we will locate the drawing on the left-hand side. As seen in the drawing, we have a total of 380 drainage fixture units being discharged at the bottom of the stack. Let's verify that the stack is sized correctly at 100 millimeters for this 6 branch intervals. We enter the table. In the 4th column, this is for more than 3 stories in height, total for the stack. We need to move down and intersect the drainage fixture unit value of 380 indicated in our drawing. Well, as you can see, 60 is not good enough. We need to go to 500. 500. We move to the left side to the horizontal fixture branch and verify that there are no horizontal branches exceeding 160 fixture units connected to the stack. And in each case, starting from the top of our drawing all the way downward, we do not have any horizontal branches connected to the stack that exceed 160 fixture units. So far, so good. Now we move further to the left all the way to the first column and properly size the diameter of pipe. Our lowest pipe on the stack is 100 millimeters, accordingly carrying all 6 branch intervals to that portion of the stack. Table 8.6.15 that was referenced in our previous section is titled Maximum Number of Fixture Units That Can Be Connected to Building Drains and Sewers. This is the table that we utilize to size the piping from a stack or multiple stacks to convey it horizontally in the form of a building drain and sewer. The first column of this table gives us the diameter of the pipe in millimeters. The body of the table is dependent upon the fall or the slope of the horizontal pipe. Within the body of the table is given the number of fixture units according to the slope of the pipe. As an example, using table 8.6.15, provide the minimum size building drain pipes based on discharges from stacks A, B, and C. Our drawing, indicated on the left-hand side, shows the most upstream portion of the building drain pipe that has an initial load of 40 drainage fixture units from stack A. So stack A enters a horizontal drain and discharges into a portion of the building drain at 40 drainage fixture units. From that point, it conveys the discharge to the left and picks up another 110 drainage fixture units from stack B. So from stack B to stack C, we now increase the load or the capacity to 150 drainage fixture units. Moving further to the left, we pick up another 65 drainage fixture units and convey that horizontally at a load of 215 drainage fixture units on our building drain pipe system. So let's start at stack A, 40 drainage fixture units. We come into the table as indicated on the right-hand side. We go to the value of 1 per 100 as a slope. From that point, we move downward to 180 fixture units. That satisfies 40 drainage fixture units. So from that point, we move horizontally to the left and size the segment of the building drainage pipe between stack A and stack B at 100 millimeters. Our next segment of building drainage pipe is between stack B and stack C. This has a fixture unit value of 150 drainage fixture units. Again, we come to the table and utilize the slope of 1 in 100. Move down, we need at least 150 drainage fixture units, and as you can see, it's the same value that we used previously, 180. Move to the left-hand side, and that pipe between stack A and stack C is 100 millimeters. That is sized adequately to take that fixture unit value. The very last segment that is beyond stack C is now 215 drainage fixture units. 215 drainage fixture units. We move back to the table at a slope of 1 in 100. We're looking for a value of at least 215. 180 will not do it here. We move down one value lower, and we come up with 700 drainage fixture units would be adequate. We move to the left-hand side to size the diameter of the pipe, and in this case, the pipe, after stack C, to carry 215 drainage fixture units must be properly sized at 150 millimeters accordingly. Section 6.10.3 titled Size of Vent Piping. More specifically, Section 6.10.3.1 gives us the requirement for the size of vent piping shall be determined from its length and the total number of fixture units connected thereto in accordance with Table 8.6.16. When we look at Table 8.6.16, this is a partial view of the table titled Size and Length of Vent Stacks and Stack Vents. The sizing criteria for stack vents and vent stacks are based on three variables here: the developed length of the vent, the size of the stack served by the vent, and the total drainage fixture units connected to the stack. A further look at the table in the first column gives us the diameter of soil or waste stack in millimeters. The second column gives us the total fixture unit that could be connected to that particular stack vent or vent stack. Finally, the third column gives us the maximum developed length of the vent in meters for diameter millimeter of vent pipes. So in the lower level of the third column, these are the values of the developed length in meters. The vent pipes are indicated horizontally across from 30 millimeters all the way to 300 millimeters. An example using Table 8.6.16 provide the minimum required vent stack size. According to our drawing, we have a multi-story building. We have a vent stack indicated with a vent terminal and a total developed length of 45 meters. So we have a drainage stack of 100 millimeters. We have the total fixture unit connected to the drainage stack of 520 drainage fixture units. And again, we have a total developed length of our vent stack of 45 meters in height. Applying the table is as follows. The first column, we select the diameter of soil stack. In this case, we have 100 millimeters. Once we select the 100 millimeter waste stack, we move to the next column to the right, total fixture unit connected to the fixture. In this case, we have a total connected fixture unit value of 520. I intersect the 100 millimeter with 540, which is adequate in this case for our application. It does not exceed 520. I'm well below that and acceptable for use. From this point, I move further to the right-hand side. What we are looking for in this case as we move horizontally is the maximum developed length of the vent in meters. Going back to our drawing, we have a total of 45 meters for developed length. According to our table, moving horizontally, we have a maximum developed length for this at 45.5 meters. I then rise above and can adequately size my vent at 75 millimeters. Therefore, what this table has done for us is allow us to adequately size the vent stack according to the diameter of our soil stack indicated in the drawing, the total fixture unit connected to the soil stack, and the developed length of our vent stack. In all cases, we have verified this and sized it accordingly to 75 millimeters at a minimum. Table 8.6.17 is referenced according to section 6.10.3.2. The branch vent shall be sized in accordance with that particular table, 8.6.17. We look at this table. This is a partial view of the table titled Minimum Diameter and Maximum Length of Individual, Branch, and Circuit Vents for Horizontal Drainage Branches. So the sizing criteria is very specific in this table, again for individual, branch, and circuit vents. They're based on three variables: the size of the horizontal drainage branch, the slope of the horizontal branch, and the developed length of the vent. The first column of this table indicates the diameter of the horizontal drainage branch in millimeters. The second column gives us the slope of the horizontal drainage in millimeters per meter. And then the last column gives us, in the lower area, the maximum developed length of the vent in meters, and across the top, again, just like the other table, gives us the minimum diameter of the vent pipe in millimeters, ranging from 30 millimeters all the way up to 250 millimeters. An example using table 8.6.17 provide the minimum required circuit vent pipe diameter. In our example, we have a circuit vent that is utilized in a horizontal circuit vent arrangement draining a battery of water closets. The diameter of the horizontal branch in this case is 100 millimeters. The slope of the horizontal branch is 10 millimeters per meter. Our total fixture unit connected is 48 drainage fixture units. The developed length of the circuit vent in this case will be 45 meters. Applying the table, we move to the first column and intersect it with the diameter of our horizontal drainage branch. For our example, it is 100 millimeters. We move to the right, and the slope of the horizontal drainage branch indicated in our example is 10 millimeters per meter. We move to the right-hand side to the developed length. As you can see, the maximum developed length for this arrangement is 58 meters. Our developed length is only 45 meters. This would apply, so we rise vertically and size the circuit vent at 50 millimeters accordingly. This is the end of the presentation. Thank you for your participation.